Hello, everyone. I am Yuqi Xue, a first-year PhD student from University of Illinois, Urbana-Champaign. In this talk, I will present IceClave, a trusted execution environment for in-storage computing. So this work was done in collaboration with researchers from University of Maryland and SK Hynix, and my advisor, Professor Jian Huang. So nowadays, we have get used to host-based computing, where we read data from the SSD and performs computation on the host. However, as we increase the size of the data, I/O becomes a bottleneck. In-storage computing, on the other hand, enables computation offloading to the SSD. So in this way, we can alleviate this I/O bottleneck and exploit the internal bandwidth of the SSD to further speed up data processing. So in-storage computing becomes a promising technique for I/O-intensive applications. And also, in-storage computing is naturally supported by the SSD architecture. So now let us take a quick look at how this happens. So a modern SSD device has an SSD controller with embedded cores and off-chip DRAM. This naturally enables us to run in-storage applications on the embedded cores and also write intermediate data to the DRAM. Also, there are a set of flash controllers, each of which is connected to a channel of flash chips. And these flash channels can operate independently to provide massive parallel internal bandwidth for the in-storage applications running on the embedded cores. So how exactly do in-storage applications access the flash memory? This is enabled by the flash translation layer, as I will explain right now. So because of the physical characteristics of flash memory, we can only perform out-of-place updates. And so in order to manage this complexity, there is an indirection layer, which we call the flash translation layer, or FTL, that also runs on the SSD controller. The FTL performs address translation in order to track the latest version of a flash page due to out-of-place updates. It also conducts garbage collection to reclaim old data. And also, because flash blocks have limited lifetime, the FTL performs wear leveling to balance the lifetime of each block. And based on this architecture, many frameworks have been developed in order to facilitate the development of in-storage computing. For example, Biscuit builds a MapReduce style programming model to enable efficient task scheduling for in-storage applications. Willow also develops a lightweight operating system on the SSD controller in order to support RPC-based function offloading, as well as running multiple user applications on the SSD. In industry, Samsung has also developed smart SSDs, which places an FPGA accelerator inside the SSD to further speed up computing. Most of them focus on performance and programmability, as we see, but the problem is few of them consider security as a first-class citizen. So why should we consider security for in-storage computing? Let me give you a simple example to see why. So let's say we offload multiple applications to an SSD. And if one of them contains malicious code, this malicious application may attack co-located applications and steal other users' data. It can also attack the flash translation layer and conducts further attacks, such as stealing other users' data or even destroying the data. And even worse, a malicious cloud platform operator, which has physical access to the device, can conduct physical attacks against the SSD, such as bus snooping or man-in-the-middle attack that intercept board-level signals. Therefore, all these security threats make us believe that it is desirable to build a secure in-storage computing environment. So to overcome these security challenges, there are some existing frameworks for creating trusted execution environments. For example, Intel SGX enables TEEs on the host processor, but SGX is not available for SSDs. On the other hand, ARM TrustZone technology can be supported by the ARM processors that are already inside SSDs, but it is still unclear how to apply TrustZone to in-storage computing. And what's more, neither of them can defend against all types of attacks that are faced by in-storage computing. In particular, SGX cannot secure data access to flash chips, while ARM Trust Zone does not protect against physical attacks at all. And both of them also suffers from significant performance overhead, which cannot be afforded by the SSD controller due to hardware resource constraints. So these problems and challenges motivated us to design IceClave, which solves the security challenges with minimal overhead. Briefly speaking, IceClave is the first trusted execution environment specialized for in-storage computing. It protects the flash translation layer from malicious in-storage applications. It guarantees data security isolation between in-storage applications. It also provides data security against physical attacks. So it is not an easy job to design IceClave, and indeed, we face the following challenges. First, the SSD controller only provides a bare metal environment. And this means there's no operating system or any other software infrastructure support for security isolation. So it will require a lot of efforts to enable security isolation between in-storage applications and the FTL. So another challenge is that providing efficient flash access for in-storage applications may cause significant overhead because isolating FTL from the applications could potentially downgrade flash access performance. Furthermore, securing flash access against physical attacks may incur more overhead. And also, the SSD controller only has limited hardware resources, such as chip area and power budget. Therefore, IceClave needs to be as lightweight as possible and should not cause significant performance overhead or consume too much hardware resources. So later, I will explain how IceClave overcome all these challenges. But before we dive into the design, it is important that we keep the threat model in mind. As we have mentioned, there are two possible kinds of attacks. First, a malicious in-storage application can conduct software attacks against co-located applications or against the flash translation layer. And second, a malicious cloud platform operator may conduct physical attacks, such as bus snooping or man-in-the-middle attack, to compromise user data. And similar to SGX, we assume that processor chip is secure against physical attacks. This is because it is very cumbersome in reality for the attacker to snoop the electrical signals that are inside the chip. We also assume that the host runtime and host to SSD offloading channel is secure. And this is because orthogonal techniques such as trusted execution on the host and secure remote procedure call are already available in modern cloud platforms, and they are compatible with IceClave and can be deployed along with IceClave. So keeping this threat model in mind, I will explain how IceClave prevents all these types of attacks we have just mentioned. So first of all, IceClave protects the FTL from malicious in-storage applications. As we have mentioned, if a malicious application gains control over the FTL, it can then easily compromise other users' data and causing severe data breach. To prevent this from happening, we can leverage ARM Trust Zone to create a secure world and a normal world. The Trust Zone hardware guarantees that programs running in secure world have full access to the entire memory space, while programs running in normal world will have no access to the secure world at all. Then we can place the flash translation layer in secure world and all the in-storage applications in normal world. In this way, a malicious in-storage application will have no access to the code or data that belongs to the FTL. However, this design will cause significant performance overhead. As an example, when an in-storage application wants to access the flash memory, it needs to invoke the FTL for address translation because we do out-of-place updates to the flash memory. And this means a context switch will happen between the normal world and secure world in order for the application to access the address mapping table to find the latest page in the flash memory. So because of this, frequent access to flash memory will cause significant overhead, which greatly downgrades the performance. So to overcome this challenge, we come up with the following design. We introduce another protected memory region and put the address mapping table inside the protected region. And we enforce that applications running in normal world can only have read-only access to the protected region. In this way, the in-storage applications can query the address mapping table, do the address translation, and access flash memory without context switching to the secure world, while security is also guaranteed for the address mapping table and the FTL, because a malicious application cannot tamper with the data inside the protected region. With this more fine-grained memory isolation, IceClave achieves both security of FTL and efficient flash access for applications at the same time. So now we have secured the FTL from in-storage applications. The next thing we do is provide security isolation between in-storage applications in order to protect a benign application from the attacks from a malicious application. So this means we'll enforce memory isolation between different applications. First, we want to provide memory isolation in DRAM. And recall that we have secure region, protected region, and the normal region. And each application can only have full access to its own allocated memory region inside the normal world. Accesses to other memory regions without proper permission will result in a page fault. So we leverage ARM processor's memory management unit to enforce such isolation at page granularity. And we also develop a lightweight IceClave runtime to allocate memory and manage application's metadata, such as memory access permissions and application identity. So second, we also enforce isolation between different applications in flash memory. This is to prevent a malicious application from probing the address mapping table entry and access other users' data in flash memory. And this is done by including the access permissions for each application in the address mapping table, and to enforce flash access control when the application wants to access flash memory. Since the address mapping table is protected in the protected region, a malicious application cannot manipulate the table to nullify the access control. And in this way, IceClave enforces security isolation between different applications, both in DRAM and in flash memory, by leveraging existing hardware on the bare metal ARM processor with minimal overhead. So now we have protected applications and the FTL against all types of software attacks we defined in our threat model. But recall that we still have a malicious cloud platform operator which can conduct physical attacks to steal user data. And in particular, there are two off-chip data flows that can be hijacked by the attacker. So first, when the application wants to access data in the off-chip DRAM, the malicious cloud platform operator can conduct bus snooping or intercept the onboard signal to compromise the integrity and the confidentiality of data. The same thing can also happen when the application wants to read data from flash chips. Therefore, IceClave needs to protect against these two attacks. And the first thing is to protect the confidentiality, integrity, and freshness of data in the off-chip DRAM. So to guarantee integrity and freshness, state-of-the-art system uses a Merkle tree. The root of the tree is securely stored inside the processor chip and free from physical attacks. And the integrity and freshness of each level of the tree guarantees the integrity and freshness of the child level. And going all the way down of the tree, the leaf nodes of the tree finally protects the integrity and freshness of the data blocks in memory. Together with this Merkle tree, in order to provide confidentiality of memory contents, a common approach is to use split counters to encrypt memory at cache line granularity. So split counter uses the concatenation of major counter and a minor counter to encrypt each cache line. And the purpose of minor counters is to mitigate memory write overheads. However, this is less of a concern for in-storage computing because we observe that in-storage programs are mostly read-intensive. And furthermore, these minor counters take up precious memory spaces inside one counter block. And this greatly downgrades the performance because for each memory read operation, the processor needs to fetch a lot of useless minor counter. Therefore, we need to redesign the split counter in order to optimize the performance for in-storage computing. And based on this insight, we propose a hybrid counter design. In IceClave's hybrid counter design, we maintain two Merkle trees, one for read-only memory and the other for writable memory. The writable Merkle tree remains the same as that of the split counter design to optimize for memory writes. On the other hand, the read-only Merkle tree removes all the redundant minor counters and instead pack more major counters in one counter block. By doing this, one counter block is now mapped to more memory data, so counter fetching can incur less overhead. This improves the memory read performance and generally improves the overall performance for in-storage applications, as we will demonstrate in the evaluation. So this new hybrid counter scheme also requires only minimal hardware changes compared to split counter. This includes a new register to store the on-chip read-only root, as well as a little bit of extra logic to maintain the different counter format. So now we have protect the data in off-chip DRAM against physical attacks. However, IceClave still needs to protect data access to the flash chips. And this is done by deploying a lightweight string cipher engine to encrypt the data flow between the SSD controller and the flash chips. So string cipher has a very good performance in general, and it has a very low hardware overhead. But it requires that the same initialization vector cannot be used more than once. And we achieve this by using a pseudo-random number to guarantee temporal uniqueness and the physical flash page number to ensure spatial uniqueness of the IV. For more details about the string cipher engine design, please take a look at our paper. So now we have all these design components, and putting them all together, we have the following architecture for IceClave. So to mitigate physical attacks, we added the memory encryption engine and the string cipher engine, as we have just discussed. Also, we developed the IceClave runtime to leverage ARM Trustzone technology and implement security isolation. We also built a host-side IceClave library for users to offload their applications to the SSD. And altogether, IceClave enables the following workflow for an in-storage application. So first, the host offloads the application, and then the IceClave runtime creates a TE for that application. And the application can access the mapping table and the flash memory efficiently without context switching to the secure world. And only if the mapping table entry is missing from DRAM, the FTL is invoked to fetch the entry from the flash memory. And then data can be securely loaded from the flash chips to the TE. And finally, the host can get the result from the application, and the IceClave runtime terminates the TE. So finally, to evaluate our design, we implement IceClave in simulators and conduct sensitivity analysis. We also develop real system prototype on FPGA board in order to verify the core functions of IceClave. We run several data-intensive workloads, including synthetic ones, as well as real-world workloads that are typical for in-storage computing. And we evaluate the following systems. First, host-based computing without security. And second, host-based computing with SGX, which provides similar but less security compared to IceClave. And third, in-storage computing without security. And finally, IceClave. So on average, IceClave introduces only 7.6% of overhead compared to in-storage computing without security. And in particular, we observed that for most read-intensive workloads, hybrid counter introduces negligible overhead due to our optimization for read-only pages. While for workloads with more memory writes, hybrid counter introduces more overhead as we expected, but well, it is still faster than host-based computing. And overall, IceClave introduces minimal overhead while providing strong security for in-storage computing. More sensitivity analyses are also available in the paper. In summary, IceClave is the first trusted execution environment for in-storage computing. It provides security isolation between different in-storage applications, and it protects the FTL from malicious software attacks. It also provides data security against physical attacks. IceClave outperforms the host-based computing by 2.3 times while guaranteeing strong security. Thank you for listening. Please read our paper for more details.